Okay, let's start next session with talk by Yuri Pautonin about our current understanding of ultraluminosity resources.
Not only ULXs, but ULX pulsars. Okay, so good afternoon. So I was asked to talk about ULX pulsars. ULXs, actually, so the plan of the talk is the following. I will spend a few minutes on talking about ultraluminous X-ray sources in general, just a few general properties. And then I will switch to the new development in this field, ULX pulsars. I will describe some observed properties, and then I will discuss our theoretical understanding of these sources. I don't think we actually understand how they radiate, but at least what we think we know about them. So ultraluminous X-ray sources actually were discovered already in the 80s with the Einstein Observatory. And these are bright X-ray sources in nearby galaxies which are not in their center, so these are not active galactic nuclei. And the definition was that they should exceed the Eddington limit for stellar mass black hole, 10 and 20 solar masses, because those mass black holes were expected to be the maximum possible that we should get from the stellar evolution. Now, of course, we know with discovery from LIGO that we actually do have more massive black holes, up to 30 or even more solar masses. But as we see easily from this picture of the antenna galaxies, that actually ultraluminous X-ray sources are associated with star-forming regions. We see that the X-ray sources, which are here on the right-hand side, and the star-forming regions actually are sort of situated close to each other. We don't know whether, or we cannot prove that X-ray sources are within the clusters, but there are some associations. Probably they have been ejected from those clusters at some point of in the evolutionary stage. For the last probably 20, 15 years, people have been talking about various models for ULXs actively, and most of these models were divided into two classes. Either these are high accretion rate stellar mass black holes, because one expects that the black holes have high Eddington limit, so that it would be easier to exceed the Eddington limit by a factor of 10. Or these are sub-Eddington accretion on intermediate mass black holes. And I'll mention immediately that there are any indications that intermediate mass black holes actually contribute to the majority of ULXs. Probably some of the brightest sources could be remnants of, or the black holes from some tiny galaxies, but most of the sources are clearly not intermediate mass black holes. There were also suggestions that this could be related to supernova, like supernovas and young rotation-powered pulsars, but one doesn't expect that these sources will be strongly variable, and we see actually that ULXs are strongly variable. Already in about 2010, there were discussions in our group that some of them could be X-ray pulsars accreting at high rates. And actually, already if you go to the old papers by Basko and Sunayev in the 70s, people have been discussing that the neutron stars can easily exceed the normal Eddington limit by a factor of 10. If you have, so basically most people agree that most of the sources are super Eddington accreting stellar mass black holes. And then you do expect that the accretion disk around these sources will not be a standard one, but actually there will be advection and there will be winds. And already in the classical paper by Shakur and Sunayev in 1973, this is a picture from there, they predicted that if you have a very super Eddington rate, you will produce a wind, and actually what the central source will accrete, it will be just about Eddington. This model didn't account for advection. If you do account for advection, then in principle you can get a high accretion rate. So instead of having, let's say, 1,000 Eddington, you can have 500 Eddington to the central source, and the rest will be ejected in the form of the wind. So this is the prediction, the dashed line, how the accretion rate will change with the radius for in the Shakur-Sunayev model, but actually including advection, you can get different values for the final accretion rate. So, but this is concerning the black holes. Of course, if you have neutron stars, the situation will be different. And 3 years ago, actually, the situation has changed dramatically. And in the paper Nature by Bacchetti et al., it was discovered, with the New Star Observatory, discovered that M82X2 source, one of the brightest sources in this star-forming galaxy, is pulsating. So actually, people looked for pulsations for some of the sources with XMM Newton. I asked Mike Revnivtsev and Alexander Lutavinov in 2010 also to look for pulsations in some of the sources, but we didn't find any with XMM Newton. But recently, actually, 2 more sources were discovered in the archival data with XMM Newton, and then also with the New Star. So I will briefly now go through each of those 3 sources that we now know they're pulsating. So we identify them as accreting pulsars, accreting neutron stars. And so this is the figure from Bacchetti et al., was shown the pulse flux as a function of time here, and one sees, so this is the pulse profile here, almost sinusoidal. And then the pulse fraction, what is important, that pulse fraction is about 20 or even 30%. So these are strongly variable sources with the nearly sinusoidal profiles. On the upper graph, you see the variations of the period as a result of the orbital motion of the source. And for this source, we know that the period is, orbital period is 2.5 days. So one measures the mass function, and one can get that the companion mass for reasonable inclinations is, because we don't see eclipses, is about 5.2 solar masses. So if you take a normal like neutron star with 1.4 solar masses and the companion more than 5 solar masses, then one understands that in this situation, accretion is unstable. You have more massive companion transferring mass to the less massive object. So actually the system shrinks, and you will have a very high accretion going through the Roche lobe. So like in SS433 in our galaxy, probably, which accretes at 5,000 Eddingtons or something like that. So if you look at the variations of the period, now here the variations are corrected for the orbital motion. So these are real variations of the pulsars. You see that there is a spin up generally, so the period is decreasing. If you look in this red box here, sometimes there is actually a small spin down, basically the spin up rate is quite high compared to the normal X-ray pulsars. And this rather high spin up actually tells you something about that these are these sources actually accrete a lot of mass. From the period over period dot, you can estimate the time scale that the source should come sort of to the equilibrium, which is just a few hundred years. And if the typical time scale of the evolution of the system maybe 100,000 years, you don't expect that we should be far from the equilibrium. Probably we are close to the equilibrium. And therefore, if you're close to the equilibrium, there are 2 torques. That is a magnetic torque that tries to decelerate the star, and the accretion torque that tries to accelerate the stars. These 2 torques actually should be in balance. Therefore, the accretion rate, the P dot that you measure, in reality doesn't tell you much, because it's this P dot is a result of combination of 2 torques of different signs. Therefore, it's very difficult to say anything from the P dot about the accretion rate and about the magnetic field, basically about the size of the magnetosphere and how much angular momentum you transfer to the star. But the maximum observed P dot actually gives you the lower limit on the accretion rate. So because the maximum spin-up torque is just the accretion torque, which here you have put the rotational radius in the accretion disk, and you can estimate from the P dot just M dot. And for example, M82X2, for the measured maximum possible measured P dot, you will get the accretion rate. Of course, there should be some absolute value of this. Is a few times 10 to 18 grams per second, which is not actually much. It just gives you just few times the Eddington luminosity, and you observe the luminosity, which is actually much higher. These are 10 to 40 ergs per second. So here you have the light curve from the paper by Sergei, luminosity versus time. And there's 15 points here, and as you see here, these points are in two different states. The bright state is about 10 to 40 arcs per second, and then there's a quiescent state, sort of, which is 50 times, the luminosity is 50 times weaker. That you see there is X2 here, it's completely basically disappeared, and here it's very bright. So, and this strong variability of the source can be interpreted as the signature of the propeller effect, as we interpret in this paper. And this would also then mean that the source is close to the equilibrium, so where the magnetospheric radius is close to the gravitational radius. Otherwise, of course, it's very difficult to change luminosity by a big fraction, by a big factor. Here, the interpretation is that once the accretion rate drops below some critical value, the magnetosphere becomes larger than gravitational radius, and then this neutron star starts working as propeller, as Sergei explained in his talk, and the accretion stops. Therefore, you expect a huge drop in the luminosity just because the efficiency of accretion now, the matter doesn't fall into the neutron star, but actually it stops at the magnetospheric radius, which is 100 times bigger than the star. Okay, so this huge variability in the luminosity is actually, as we will see later, is a characteristic of this all of these sources. So another source was discovered just last year. The paper appeared this year. This is ULX1 in AGC 5907. It was discovered in the search of the archival data. And here you see the XMM data from 2003, XMM data from 2014, where the signal is very, I think the discovery was this data. But then if you can correct for the P dot, then you will see that there is actually a huge spike in the power spectrum density. And in individual observations, you can actually measure P dot here, which is very large. Here is 10 to minus 8. Of course, this P dot is very difficult to say that this actually is related to the spin up of the star, just because we don't have the orbit for this object. So this could be related just to this change of the period can be related just to the orbital motion. But then, there is a secular trend on the time scale of 10 years, because you see the period was, in 2003, it was 1.42 seconds, and now in 2014, 10 years later, it was 1.14 seconds. So clearly, if you just compute what is the change of the period in this 11 years time scale, you will get this value, which is about 10 to minus 9 seconds per second. And this gives you directly also the measure of the minimum possible accretion rate that you can have. So this is for this source. I put here the larger value, which gives you very super Eddington accretion rate. If you put 10 times smaller, of course, you will still have accretion rate, which is tens of the Eddington values. What's interesting that this 5907 shows also strong periodic variations, and here you have, which is interpreted as probably superorbital, the period of 78 days, and you see that there is a nice sort of light curve that goes for a few years, and sometimes there are drops here in the light curve, and it's easy to see in this paper from Israel. You see that there is a typical luminosity of this source is now 10 to 41 arcs per second, the observed luminosity. Sometimes the source is completely unobserved, so the luminosity drops by a factor of 100. So also there is a huge change in the luminosity. Okay, the spectrum of the source is sort of thermal, that cuts off at somewhere 10 keV. And these kind of spectra also are typical for ultraluminous X-ray sources, all of them, and ultraluminous X-ray pulsars in particular. And even from the shape of the spectrum, from the peak of the emission, you can say something about the emission region, the size of that. Because if you have 10 to 41 arcs per second, and you have the temperature of the plasma, of the color temperature that you observe with the radiation is, let's say, few keV, the effective temperature is probably smaller, so therefore you immediately say that the size of this emission region should be a few stellar radius, maybe 3 stellar radii or so. So it's not very large, but it can be very small polar cap at the neutron star surface. Then the third source is object in the galaxy GC 7793. This is another paper by Israel. Here you see the pulsation, the peak in the power spectrum density and the pulse profile. And for that source too, you see huge variations in the luminosity. There is a peak luminosity there, which is about 10 to 40. And then there are sometimes it's not observable at all. There is also a circular trend, but here the P dot is quite small. And in individual observations, you cannot even detect that, basically. What's interesting, so here's the luminosity. You see that it's in the bright state, it's about 10 to 40 arcs per second. What's interesting that this source also shows variations about the same time scales, 65 days. And it could be also superorbital. And some people claimed first that this is orbital variations, but this paper by Hu actually claimed that it's probably superorbital. Then the orbital is probably between 3 and 7 days, similar to what we have for MIT2. Well, it was 2.5 days. But, again, the pulse fraction is also very large. Here it's about 30% for this source. So here's just the ULX pulsars in a nutshell. That's the most important things to keep in mind here is that all the sources have large pulse fraction, 20–30%. There is huge variations in the luminosity by a factor of 100. The period is about 1 second, and the luminosity is been like 10 to 41, 10 to 40, 10 to 41. Okay. Now I will switch to some more theoretical interpretation of what we think is happening. First, let me remind you 3 characteristic radii that you expect, we need to work with. One is the radius of the rotation, where the accretion disk rotates with the same velocity, angular velocity as the neutron star. And for 1 second period, we have it's 10 to 8 centimeters. So basically, it's 100 stellar radius. Second important radius is the spherization radius. You do expect, when you have high accretion rate, much above the Eddington, the accretion disk itself becomes Eddington at some point. So you have a luminosity exceeding Eddington at some point. And at this radius, one predicts that there will be a wind launched. So everything within this spherization radius, the mass will be lost. So the accretion rate after that will not be constant. And for example, for M82X2, where the luminosity is about a few hundred Eddingtons, you put here a few hundred, you get the spherization radius about almost exactly in the same place where we have the rotation radius, 10 to 8 centimeters. So this is the radius of the star here. Okay, and the third radius is the magnetospheric radius, of course, which depends on the accretion rate as well as the magnetic moment here, mu. There are some coefficient here which depends on the disk structure, whether it's gas pressure dominated or disk pressure dominated, and all the complications. And this is not really well-known coefficient. But anyway, so amazingly, that because we expect that all of the sources are close to rotation, the magnetospheric radius should be close to rotation radius, and actually for the accretion rate of a few hundred Eddington, even spherization radius will be close to that. Okay, so this is the picture from Kulkarni and Romanova. It was for the millisecond pulsars, but general picture is still the same. You have accretion disk probably slightly thicker than standard thin accretion, like gas pressure dominated thin accretion disk. And then you have the gas follows some curtain and follows into the poles of the star. And when, of course, the star rotates, you see the pulsations. But where the radiation is coming from, of course, it's not from the surface of the neutron star, as in the case of accreting millisecond pulsars that Alessandro was talking about, but from all this curtain, from all this accretion column. Okay, so one of the most discussed questions in this business is how to interpret the luminosity that you see. Is the 10 to 40 ergs per second, or even 10 to 41 ergs per second, is the real luminosity of the source, or it is the luminosity that is actually you observe only, and other observers see almost nothing? So whether the radiation is actually strongly beamed. People have been discussing this beaming in the context of accreting black holes, where you do expect acclimation of this by the wind, by a factor of maybe 10. For the neutron stars, the situation obviously has to be somewhat different, because the magnetospheric radius is 100 times the stellar radius. Therefore, it's very difficult to launch the wind, just because the the accretion disk stops at much larger radius. And in the papers by Kingal and Asota, in a couple of papers, they still assume strong beaming. And by assuming strong beaming, you reduce the requirement for the accretion rate by some factor, not by a factor of 10, 20, by a factor of 5. Because if you reduce, so basically by assuming strong beaming, you say that the neutron star get much smaller luminosity by a factor of, let's say, 10 to 20. So it's just a little bit above Eddington. Okay. But the accretion rate is in reality about 40. So when the matter, a lot of matter goes in, at spherization radiuses start to be blown away, and you lose 90% of this material into the wind, which collimates the radiation. Okay? And only 10% falls to the neutron star. So for this model to operate, they require, in the paper from 2016, for example, that magnetospheric radius is very small compared to the spherization radius and rotation radius. And then magnetic field that you get for that, if you assume the small magnetospheric radius, is just 10 to 11 Gauss. Okay. Here in this model, specific model of this 2016, of course, the question first arises, how do you get huge variations in the luminosity? Because you don't expect that the accretion rate will react very rapidly and in the outer accretion rate in the accretion disk react very rapidly, and you change m dot by a factor of 100. So it's very difficult to imagine. And of course, then another question is, if you have collimation by the wind, how you can get a big pulse fraction and how you can get sinusoidal variations. There's no model for that. You want to just assume that you have some radiation from the pulsar, which is reflected from the walls of this funnel and collimated towards you. But naively, you wouldn't think that you will lose pulsations because you don't expect that there is a laser beam as this wine pointer that shines on the walls of this funnel. But you expect rather broad emission pattern from the accretion pulsar, and therefore you will lose most of the pulsations. So personally, I don't believe in the strong beaming by a factor of 10 and 20. Maybe there is a factor of 3 beaming, but not more. So if you don't have strong beaming, then you automatically say that, okay, your accretion rate is really tens of Eddingtons, maybe 100 Eddington. But then if you want to have a system in equilibrium, magnetospheric radius close to the rotation radius, then this automatically tells you that the magnetic field of the star should be very large. Of course, it depends still on the model of the accretion, accretion disk interaction with the magnetosphere, but it cannot be 10 to 11 Gauss. It's probably close 10 to 13 or 10 to 14 even Gauss. So for M82, so if you assume that magnetospheric radius is just close to the rotation radius at the maximum luminosity, or some 10 to 40 arcs per second, then you immediately, so the rotation radius and the magnetospheric radius relate like that. And so then you get a relation between the magnetic moment or the magnetic field and the luminosity. So the accretion rate, you say, it's just you get from the luminosity. So, and the period, which is, of course, comes in this formula. So on the y-axis, you have luminosity times the orbital spin period into some power 7/3. And you just can read the magnetic field from this graph, because there should be just relation between the magnetic field, the luminosity, and the period. There is some coefficient of proportionality. And you can test this relation on the sources where we know magnetic field. These are the sources where you measure magnetic field from cyclotron lines. SAX 1880 is a millisecond pulsar. You can sort of measure magnetic field from the spin down there when it's between the outbursts. And this theoretical relation actually holds very well. So then if you believe this interpretation that m dot is actually corresponding directly to your luminosity, then you just read off the magnetic field, and it becomes few times 10 to 13 at least. Okay. Another question that is discussed a lot is actually how to exceed the Eddington limit. Because you can supply the neutron star with the large accretion rate, 100 times the Eddington, but somehow the radiation should escape and not stop the accretion. First, of course, we should remember that even the accretion disk itself can exceed the Eddington limit, because radiation from the accretion disk goes like normal to the disk, gas flows a Lambda disk, so there is it's not so easy to interact with these photons with the disk. So standard sort of advective disk can easily go like 10 times the Eddington. Here you have another situation also. You have this accretion curtain, which could be very thin curtain, and so the gas falls down, and the photon goes sideways. So you have fan beam, sort of photons escape sideways, and the gas falls into the neutron star. So these are the papers that have discussed recently all this, or not recently even, all these ideas. Second effect that can help to exceed the Eddington limit is so-called photon bubbles. So the accreting gas becomes strongly inhomogeneous, and the photon can escape between these inhomogeneities. It's like if you accrete the bricks, then of course the bricks will not feel the same, and it will not produce the same Eddington limit as the gas. And the third effect is that if you have strong magnetic field close to the surface, then you can reduce the opacity, because at least for one polarization, it goes like energy square. And if your magnetic field is like magnetar-like 10 to 14 Gauss, then this factor E over I cyclotron energy square could be easily a factor of 10,000. So you can easily reduce your opacity by a large fraction, and therefore you can exceed the Eddington limit. Of course, this argument for the reduction of the opacity works close to the neutron star, but once you go 10 times the stellar radius, it stopped working, just because the magnetic field of the dipole field goes like R to minus 3. Therefore, at 100 stellar radius, it becomes 1/millionth of the original one, and basically there the opacity is Thomson. Then the question is, what happens to the gas that actually tries to go to the magnetosphere? So here is just to remind that where the photons are coming that you observe. Some of them coming from the surface or from the column close to the neutron star. Some of these photons can be reprocessed in these curtains, and some of the photons can come from the accretion disk, and these are the softest ones. But here still the question is, what happens to the gas? How you can push the gas towards the neutron star? Because there is a radiation force that exceeds the gravity force by a factor of 100, because these are super Eddington sources, right? Of course, the gas in this flow is confined by the magnetic field, so it's really not, the gas cannot be really pushed easily away, but still, the gas tries to fall in, but the radiation will stop it. So of course, this flow is optically thick, so therefore the radiation force that will be acting only on the surface layers of this layer, of this curtain, and the rest of this will probably not feel the radiation. But the dynamics of this is not actually, nobody has solved this problem yet. So this will be very interesting problem for some clever PhD student. So Maxim Lutikov discussed this problem exactly, and he suggested that actually our neutron star should be basically orthogonal rotator, and then accretion disk will go directly to the poles of the neutron star, and the photons will just escape sideways without really interacting with all this gas. So this way, actually, you can sort of collimate the matter in the very thin sheet, and then the photons will escape sideways. But this is an unsolved problem, actually, how you push the gas through all this curtain to the neutron star. So, So here I plot the luminosity, observed luminosity of the object versus the magnetic field, and on this diagram there are a few lines that one should important to notice. There is a line here on the top is written supercritical accretion disk. This line means that above this line, the magnetosphere becomes smaller than the spherization rate. It's larger than the spherization radius, so you have high accretion rate, and therefore you will start producing the wind. So it doesn't mean that this region is forbidden for us, but it means that you lose some material in the wind, so not everything will be falling down. There is this thick line that is prediction from some simplified model of the accretion column, like a la Baskov-Sunayev from 1976, that was produced by Alexander Moustakas. And this is a simplified model of what would be the maximum possible luminosity from the accretion column of size about stellar radii. Of course, this is not absolute limit, because you can have some effects that were not accounted for this model. Okay, and then there is this dashed line for different periods. These are corresponding to the equilibrium between the spin up and spin down. Basically, if you are below this line, then the magnetic field is too strong and there will be propeller effect. So your object should be probably below this supercritical line, probably below this thick line, but not necessarily, and certainly above this dashed line. So now if we take M82X2, this is this orange circle there, the period is 1.37 seconds, so it should be above this dashed line or at this, just because if it's close to the equilibrium. And then the sort of consistent solution will be 10 to 14 Gauss magnetic field and 10 to 40 ergs per second. If you take this object 77 in NGC 7793, luminosity is about the same. Period is smaller, therefore the spin up the propeller line is to the left. Therefore, you do expect somewhat smaller magnetic field. Otherwise, you'll be in trouble. And then for 5907, which is 10 times brighter, you're actually in trouble because it's becoming it's clearly exceeding this supercritical accretion disk line. So you have to produce the wind, and it's much above this dashed line. It's okay with the propeller line, but in order to get this object to fit into this picture, probably you have to assume some moderate beaming by a factor of 5, maybe. And this probably also means that this model of the accretion column is not the final one. Probably somehow we have to think how to produce even higher luminosity from this accretion column. Okay, so I switch to my conclusions, as my chairman tells me to do. And so the thing is to take away here is that we now know that pulsars, X-ray pulsars, can exceed the Eddington limit by a factor of 100 or even 500 at least. Even if you account for beaming, it's probably they exceeding the Eddington limit by a factor of 100. My guess is that there is no strong beaming involved, maybe by a factor of a few. We do expect that the sources are close to equilibrium, and therefore you just, from the period, you immediately can tell you what's magnetic field. And for some sources, you do get fields of 10 to 13, 10 to 14 Gauss. And probably there is a problem with the interpretation whether you can have a magnetar-like magnetic field in the objects which are probably a few million years old. Highly super Eddington accretion or highly super Eddington luminosity can be arranged using different factors, geometrical effects, reduced opacity, and photon bubbles. So that doesn't seem to be a problem. It is probably still a problem to get luminosity which is 1000 Eddingtons from the neutron star. Getting 100 times the Eddington luminosity is not a problem for sure. I think I will stop here. Thank you very much.
Now we have time for questions. Yes.
Two questions. The first one, how long such systems live, and can you estimate the asymptotic values of the spin periods using your P dot, and P dot dot?
Yeah, I think the lifetime is, people estimate, I don't think it's more than 10 to 5 years, probably 10 to 4, 10 to 5 years. So because you have accretion rate which is, 10 to minus 5 or 10 to minus 6 solar masses per year. So those systems cannot live long. Then the final period you can estimate from the magnetic field, obviously. But I think, of course, it depends on the accretion rate, if they will be accreting all the time like that.
1 millisecond, 10 milliseconds?
No, I don't think these are, because if you believe in these strong magnetic fields, you cannot go to millisecond periods. I mean, this is the difference from what we are saying. Our group says that we are close to the equilibrium. So this is basically your final period. But a group, for example, by Andrew King, they say that you have much low magnetic field. So your magnetosphere is much lower, smaller than, and then this, of course, means that you can accelerate the star much stronger. So, and then this would mean that now we are out of the equilibrium, obviously.
The second question.
That was the second one.
How your results will be changed for different inclination angles between the magnetic moment and the rotation axis?
Yeah, I mean, we haven't computed really how the how this geometry affects or the pulse profiles, or the obviously you do need some inclination to get pulsations. Otherwise, you would not have any pulsations.
But you have used the orthogonal geometry.
No,
yes?
I mean, for the estimates of the magnetospheric radius, we just used the basically aligned rotator. So, but of course, this is just estimate. You have once you incline it by some degrees, of course, you will have some instabilities. Who knows? But I don't think it will change dramatically the size of the magnetosphere.
So I was wondering, Yuri, if this condition of having the sources all at the equilibrium, it doesn't imply that you need a bit of fine-tuning, because the magnetic fields have to be such that you are always in this condition for all these ULXs. But if you decrease a little bit the field, you would still get a super Eddington mass transfer from the companion. So why do you think these sources have all such large fields such that they are in equilibrium?
No, I mean, first I think the time scale to get to the equilibrium is very short. Even for M82X2 is 300 years. For those which is 10 to 40, 1 ergs per second, if you just take this as a face value, the accretion rate is 30 years. Okay, so basically it's very short time. So basically this tells you that we have to be close to the equilibrium. Because you see in one source, you see that there is acceleration, right? So the period is changing on the time scale of 10 years. So, I mean, but, yeah. So you do accelerate them, and, yeah, I don't see how you can be far from the equilibrium, let's put it this way. Of course, I mean, we cannot prove that now, because the source is actually strongly variable, right? You said you have luminosity 10 to 40, then next time you observe it's 10 to 38 ergs per second. So what is the average accretion rate? Who knows for this source, right? So we just assume that this is the highest accretion rate, sort of defines you the equilibrium, and because it switches to this propeller effect. We believe that these huge variations are related to the propeller effect, and then that's it. Then you have to be close to the equilibrium. Yeah, I don't know whether I'm answering your question. Sorry? Yeah. So this is the model by Andrew King. So he says, he basically tells you that the accretion rate, the magnetic field is lower, so normal, right? On many, it's not only him, but many people say it's normal pulsar. Okay, this means that if you take the luminosity as the face value that you observe, then it means that your magnetospheric radius is much smaller than the rotation radius, so you're out of the equilibrium, obviously. Okay, so the spherization radius for that case is far away. So it basically, I mean, this is their model. So then you have the wind probably start blowing in, and then you can collimate. But this makes a very certain prediction that the ULX pulsars are observed at very small inclinations. Because if you have beaming, it means, which I probably forgot to mention, if you have beaming by the wind from the accretion disk, it means that your inclination is within 10 degrees. I mean, is it reasonable for all these three sources that we have all the three observed at 10 degrees from the axis? I'm not sure that it's reasonable even for M82X2. It's just the chances are small, and then just what will be the companion's mass for this case? Okay.
The question is, it seems that in the CCOs, you would need to have much higher accretion rate to bury the magnetic field than 100 Eddington. Supposedly, you have to accrete like 10 to minus 3 solar mass in a matter of hours. So how do you do that?
You're asking me.
Yeah, I mean, that's the model that they invoke, you know.
So you mean that for CCOs, in order to get low magnetic field, you have to
Yeah,
bury it?
in order to bury the magnetic field, you need 10 to minus 3 solar masses in a matter of, I don't know, several hours. That's what I was told.
So basically, yeah, one can estimate how much super Eddington it is. Yeah. I don't think it doesn't sound reasonable to me. It's maybe. I mean, cannot you have just a low magnetic field to start with? You don't need to bury to put so much mass.
That is what anti-magnets are. Yes, they keep saying that magnetic field is very tight.
Well, this is the question to the people who make the model.
Ali?
Near spin equilibrium, both the torque and the mass accretion rate onto the neutron star are likely to be strong functions of the fastness parameter. And possibly they are not the same function of the fastness parameter. So how do you justify then going from measurements of the spin down rate to place a bound on the mass accretion rate?
Okay, so I understood. So actually, our group, we put no weight on the measurement of P dot at all. Basically, there are some people who actually use the value for measuring magnetic field or the magnetosphere radius or whatever. We pay no attention to that because we believe that measured P dot is, because this is the function of two torques of different signs, the measured P dot is actually the minimum. Yeah. So okay. How should I put it? So only the maximum possible accretion P dot gives you some estimate of the minimum possible accretion rate. But the measured P dot, the small P dot, doesn't tell you anything, just because in principle, in equilibrium, you expect 0 P dot, right? So when you measure small P dot, what does it tell you? To me, it doesn't tell anything, right? But if you have measured high P dot, then it tells you that, of course, you need to have some accretion to start with. And then you can forget about magnetic torque, just because for this purpose, because this gives you the minimum possible accretion rate. That's it. Yeah. That's it.
Thank you, Yuri. And next speaker is Buck Nielsen with another super Eddington source.
Okay. Hi. I'm a PhD student at Leiden Observatory. And I'm going to tell you a little bit about why we think that the source 2A1822371 might be a super Eddington source. I'm going to start by leaving you with my conclusions, actually, because it's also the outline of my talk. I'm going to start by going through why we think that we never see the surface of the neutron star, why we think that that we have to have an optically thin or not very opaque accretion disk corona. Then I'm going to show you the long-term and short-term spin-up. And then I will move on to why we think it's a super Eddington source with probably a low magnetic field. And then if I have time, I will show you some comparisons to some other sources. But first of all, let's meet the system. So it's a low-mass X-ray binary. It's a persistent X-ray source. The pulsar has a spin frequency of about 1.7 hertz, which is about 0.6 seconds. The luminosity is observed to be about 10 to the 36 ergs per second. And interestingly enough, we find an X-ray to optical luminosity of about 20 to 60, which is quite a lot lower than what you would normally expect. Usually you would expect something like a few hundreds to 1,000s. But we do see the source edge on, so that might explain some of it. It has an orbital period of about 6 hours and an orbital period derivative of about 2 times 10 to the minus 10 seconds a second, which means that the source is moving away from the two sources are moving away from each other quite fast. And then there are two claims for a magnetic field of the source. One is about 10 to the 10 Gauss, about 10 to the 10, 10 to the 11 Gauss, which is from the group of Yari et al. And the other claim is for about 10 to the 12 Gauss from Sassano et al. And both of these claims are from cyclotron resonance scattering features at 0.7 or 30 keV. So two quite different claims, and I'll come back to that as well. We have used RxTE data over a baseline of about 13 years from 1998 to 2011. And now I will move on to the light curve and to why we don't think we see the pulsar surface, neutron star surface. So the light curve is quite interesting. It's an accretion disk corona source, an eclipsing low mass electric binary. So we see this is the eclipse, but the only part that's really not eclipsed at all appears to be around here. It's only a semi-eclipsing source. It only goes down to about half of the maximum counts. And it's thought to be an accretion disk corona source because it has these very wide sort of eclipses, very wide regions in the light curve. So we think, so it's proposed that there needs to be some sort of X-ray emitting region around the source to give these very wide features, but still only be eclipsed about 50%. So because of this light curve and because it's only eclipsed about 50%, so we always have some sort of emitting region, we were wondering if we ever see the surface of the neutron star. So we looked at the fractional amplitude for eclipsed parts. So just for the sake of argument, we defined the eclipsed parts as the entire part here, and the non-eclipsed as being the small part that has the highest count rate. So we looked at eclipsed data and the fractional amplitude of non-eclipsed data, and we see that there's not really any change over the orbital period, which means that we most likely never see the surface, but the pulsations that we do see comes from this X-ray emitting region. So all the light that we see is through this region. So then we can have a look at this region, which is the accretion disk corona. So it's proposed to be some sort of extended X-ray emitting region around the accretion disk. It would look something similar to this figure if we saw it from the side. And the inclination angle for the system is quite high. It's about 83 degrees, so we really are seeing it from the side. And the accretion disk corona is consisting of some sort of evaporated material from the accretion disk. But this made us wonder, because usually when you see the spectrum, and people fit the spectrum, this is the spectrum of the source, by the way, it's fitted with a model that has very opaque, that seems to be very opaque, or that seems to take into account that the accretion disk corona is very optically thick. But that does leave us with a bit of a problem, because if we have a very thick corona, we wouldn't be able to see pulsations. And we do observe coherent pulsations. So we wanted to try and see if it's possible to create the same shape as the spectrum that we see. So we took the best fit to the spectrum. It's a proof of concept. So we took the best fit to the spectrum, which is the red line, and we tried to upscatter it through an inverse Compton upscattering code, which is created by Giannis and Sprout in 2004, to see if we could have an optically thin corona. So instead of about a tau of like 10 to 20, we set the tau to be equal to 1, which should be thin enough that you can still see coherent pulsations. And the blue curve is sort of the model spectrum, and the black curve is what we find after we send it through this Compton upscattering code, which gives us a spectrum that is similar in shape to what we see in reality. So let's move on to the spin-up of the source. We have 13 years of data from RxTE. So we found the spin of the source in all of these data, and we find an overall spin frequency derivative of about 7.6 or 8 times 10 to the minus 12 hertz per second, which is a fairly fast spin-up. It does give us a spin-up time scale of about a few thousand years, which is quite fast. And we see some variations here and there, and because it's quite a fast spin-up time scale, we were wondering if there are any changes on a smaller time scale than just the overall long time scale. So we looked at two different segments of data that we could phase connect, one in 2001 and another set of data in 2002. And we saw that in the phase-connected data, if we don't take a spin frequency derivative into account, we see this very clear parabolic shape, which is a clear sign that there is a spin frequency derivative. And we find in these two segments spin frequency derivatives that correspond to the overall long-term spin frequency. So our source really is spinning up. So we were wondering, well, is there some explanation for this? And we compared it to some other sources. One is 4U1626 minus 67, and another could be GX1 plus 4, which both show a very fast spin-up. And then after a while, it spins down at about the same spin-up, spin-down time scale. This is one possible future for this source. However, this might not be the only possible future or idea for what is actually going on in this source, because we can also look at it as a super Eddington source. So there are some problems with just what we just found and the normal assumptions that you make about this source. And that is, for instance, that the orbital period derivative cannot be explained. So the change in orbital period, you can't explain that by a normal conservative mass transfer. So we're wondering if we can do this by assuming that it's somehow out of equilibrium, that it's transferring mass on a different time scale. And here we say that it's actually transferring mass on a thermal time scale, which would be a time scale about 10 to the 7 years. And that would give us a mass transfer rate of about 10 to the minus 7 solar masses per year, which is super Eddington. The Eddington limit is about 10 to the minus 8 solar masses per year. So we started by looking into if this mass transfer rate, this higher mass transfer rate, could explain the orbital period derivative. And we looked at the A dot over A, which is dependent on the mass transfer rate, and compared it to the orbital period derivative. And we find that to within an order of magnitude, it fits. So a super Eddington accretion rate could actually explain the orbital period derivative. So to see if this seems reasonable in other parameters, we looked at the King-Lesotho model from 2016 that Yuri Patanin also mentioned, where they look at the ULX M82X2 to see if it fits in the sort of general idea of ULXs as beamed X-ray sources with low magnetic fields, as Yuri just explained. And they estimate the magnetic field from the magnetospheric radius and the spherization radius. So we try and do the same, and we find a spherization radius of about 10 to the 7 centimeters and a magnetospheric radius of about 10 to the 6, 10 to the 7 centimeters, so approximately around the same, and a magnetic field of about 10 to the 10 Gauss, which is a bit lower than what you normally expect for the low mass X-ray binaries. but it sort of corresponds to what Iaria et al. In 2015 proposed for this source. And this, for us, would mean that we have a geometry of the source that's similar, that looks somewhat like this. So we have the neutron star in the center, and we have some sort of beamed region. And then because our magnetospheric radius and our spherization radius is about the same, the inner disk would be puffed up. And then we would have this outflow or accretion disk corona around the thin disk still. And then the magnetic field would still be low, but with some sort of beaming. We can actually test some of these things. We could look at a new star observation. So we can test if the magnetic field is about 10 to the 11 Gauss, or if it really is the claim of 10 to the 12 Gauss that's correct. By looking with new star at around 30 keV, new star should be perfect for that, and seeing if we can find the cyclotron resonance scattering feature there. If we do not, it's possibly a stronger claim for the 10 to the 10 Gauss field. Also, if this is the case, it should not be similar to the two other sources that I mentioned, to GX1+4 and 4U1626. We should not be able to see torque reversal. And we would probably have some sort of jet or outflow present in radio. And we could also look at that. And there's not really any observations in radio for this source. So that's a clear possibility. We can compare this to some other sources. For instance, SS433 has a somewhat similar geometry. It's a black hole and not a neutron star. But we still see the inner disk being puffed up, and we see some sort of outflow. And I think the source is suggested to be ULX or a possible ULX. We can also compare it to some of the other accretion disk corona sources. For instance, for U1624 or AC211, you see the same sort of light curves, sort of some of the same features. You only have the sort of 50% eclipsed. Of course, you see these things. You can also compare some of the spectra from these sources. So this is the spectrum for 21822, and we see that it has this sort of cutoff around 10 keV, which also two other accretion disk corona sources show. However, not all of the accretion disk corona sources show this cutoff, or at least we're not sure, because some of these sources have quite limited data. But we think that it might be a super Eddington source. And then I will just leave you with my conclusions. Thank you.
Thank you. Questions? More questions? If we do not have any questions, maybe we can move to the next speaker. Okay, Mikhail Garasyov. Please.
Okay. So first of all, I would like to thank the organizers for the opportunity to give a talk here on this wonderful conference. I'll present the results of our work with colleagues from Institute of Applied Physics from Nizhny Novgorod, Evgeny Delyshev and Vladimir Kocherovsky, and I will talk about the redistribution effects in the cyclotron resonance scattering. So why to study cyclotron lines at all at those times? This problem have been studied for decades, but in view of upcoming space missions like XARM, Athena, or LYNX, the detailed models of radiation transfer could be very useful to model the spectral features with high precision and to extract some physical data from that observations. Also, it is very useful if you want to study the structure of the outer layers of neutron stars' atmospheres, or want to study the radiation pressure effects in the atmospheres of neutron stars, so accretion sources. And also, in the recent paper of Rothschild, these redistribution effects was used to build a model of the outburst in accretion X-ray binary. So to feed the data, they used some model which includes the redistribution of radiation in the lines. So the transfer of radiation happens in the atmosphere of neutron stars, which is about 10 centimeters in height in physical units, and it characterizes by the wide range of temperatures and magnetic field strengths. In these atmospheres and in magnetosphere, scattering strongly dominates our absorption, and the opacity of magnetized plasma are very high near the frequencies, near the cyclotron frequencies. So the problem which I will talk about is that the resonance scattering in cyclotron lines is qualitatively different from the resonance scattering in atomic lines. So there are, in radiation transfer theory, there are several approximate methods to deal with frequency redistribution in resonant lines. As to say complete frequency redistribution, then people try to approximate the real redistribution with some functions. Basically, that tells you that photon forgot about its initial position after one scattering. The opposite case is coherent scattering, then the photon remains remembers its initial state after many scatterings, and the partial redistribution in something in between. It's the most interesting but most complex case. And I will talk about it in view of cyclotron lines. So here, the little sketch of basic view of cyclotron scattering. Here's the frequency and the propagation angle with respect to the magnetic field. You can divide basically the photons into two groups. The first group is the photons in the wing, which scatters almost coherently with little frequency shift in each scattering. And the second group is the photons in the line, which travels along some inclined lines and scatters almost coherently. They do not preserve the frequency itself, but they preserve a function of frequency and the angle with respect to the magnetic field. So this is kind of a quasi-coherent approximation. This holds exactly if you work in the non-relativistic approximations, but the deviations from this picture of quasi-coherent scattering happens if you take into account the relativistic corrections. Then the deviations started to appear from this simple picture, and this is the this is the redistribution in cyclotron lines. This is the most important effect. So in our work, we estimate different parameters, how the photons escape from the atmosphere if you take into account this kind of redistribution via the relativistic corrections to the resonance cross section. So here, for example, the result of our numerical simulations, there you can see the relative fraction of photons emitted at some optical depth tau, which will escape from the atmosphere. This is for the parameters. Then the temperature is 50 electron volts. I can stress it. I would like to stress this temperature. It's highly non-relativistic, but relativistic effects play a very important role because they allow photons to escape from the line center, which couldn't happen if you don't take into account these relativistic corrections. So here are some results of our analytical study. So the main parameter is the escape probability, which could be, in this case, which is proportional to 1 over optical depth. Not actually 1, but beta t. Beta t is the dimensionless thermal velocity in the plasma. So if you have just a diffusion escape from the atmosphere, then you have the probability 1 over t squared. So the redistribution is important if you have to escape from the optical depths higher than t dot. And if this t dot is less than the thermalization depths there most of the photons are coming from, then the redistribution effects are important in the whole atmosphere. So this happens if your magnetic field is less than 10 to the minus 4 of the critical field for the temperatures of 50 electron volts. And if the magnetic field is less than that, then the coherent scattering are working. And the quantum recoil is important if the magnetic fields are larger than the 10 to the minus 2 of the critical field. So there are 3 zones. There are different kind of redistribution mechanism and different kind of escape of radiation are working in the atmospheres of neutron stars. For very small fields, the quasi-coherent approximations is working. For the middle magnetic fields from 10 to the minus 9 to 10 to the 12, for example, it depends for sure on temperature. The approximations, the partial frequency distribution is important. And if you are working in the high magnetic fields, then basically complete frequency distribution are working because the recoil is very large and it just strikes the photon out of the resonance via one scattering. So all these calculations could be applied to the radiation transfer problem, but you have this is high-dimensional, usually equations, and it's hard to solve them completely. You can use some approximations. It's very useful to derive some function, some approximate function which describes the distribution effects. Sorry. So it was done by us recently, and some preliminary results with the modeling of radiation transfer in the atmosphere we obtained here. The test of our redistribution function, comparison of our approximate redistribution function with the exact one. So it kind of okay. Yes, and we used this redistribution function in order to obtain some spectra of escaping radiation for 2 different modes. But these results are quite preliminary, so it couldn't be used to fit some data up to the moment instead. So, and this is instead of conclusion, some summary of frequency redistribution effects that could happen in cyclotron lines in neutron star's atmosphere. Yeah, my sketching skill leaves much to be desired, but nevertheless, you can work. If you have a small magnetic field, you will work in the coherent approximation, and the escape probability then 1/T squared. Then if the magnetic field is higher, then the partial redistribution are important, and the escape probability is beta T other tau. And if the complete redistribution is working, this is then recoil is important, for example, then escape probability is 1/tau. So that's all. Thank you.
Thank you. Questions? Again, no questions. George?
Well, just a note, if you want to consider this problem seriously, deploying to real situation, you at least should consider together the distribution not only over frequencies but also over angles and polarizations. Are there any polarizations in your equation at all?
For sure, you should consider the polarization, but this is a separate work because this will work for any polarization if the scattering happens.
No.
But no. But and the problem, if you want to have real transfer equations to solve the real transfer equations taking into account the distribution of the angles and other the frequencies, then you have to check that in these limits your distribution function on the grid works as described by these analytical results, and no numerical, because it's very hard to constrain the redistribution function on the grid, which will hold that result, because most of the redistribution happens in the angles almost perpendicular to the magnetic field, and you have to have very fine grid in your radiation transfer equations near these frequencies and angles, and this is very hard work. So,
of course, no doubt, it's not an easy work.
Yeah, so this is like a scheme what to expect in real radiation transfer simulations if you want to include these effects into account. Yeah, just because of this small angle problem, this is very hard to construct.
Yeah, okay, thank you.
More questions? Yes?
A small note that indeed in our paper with Rothschild we used we neglect logarithmic dependence in your formula, but basically we used partial redistribution in your terms function for escape probabilities, and it is only in this case which observations can be fitted. I mean, the change of the cyclotron line position with X-ray flux, which were obtained from observation. So, basically,
but logarithmic dependence is...
Yes, logarithmic dependence is
very, very weak.
Yes. So it's a confirmation from other side of your results.
Okay, more questions? If not, let's say, Mikhail.
Whoa. Okay. Let us start the last session of this conference. To start this last session, I would like, first of all, to congratulate our guests from France and of French origin of national holiday. And now I'm passing, to the first talk in this session, Cal Parfrey. 25 minutes, including questions.
Okay, thanks. All right, so I'll be talking about the interactions between magnetized rotating neutron stars and accretion flows. And I'll primarily be talking about interactions with millisecond pulsars. So we heard a lot about these today in various flavors that they come in. Primarily the accretion-powered sources, which accrete via these magnetically funneled accretion channels. We'll be hearing more about the nuclear-powered sources, which are observable through their X-ray bursts in the next talk from Yuri. And then we also heard this morning from Alessandro about these very interesting transitional systems, which we see in more than one state, so the X-ray pulsar state and the radio pulsar state. Because we see them in the two very different manifestations, hopefully we can learn different things from each state and learn more about both these systems and all the other accreting millisecond pulsars in general. So these systems pose many observational puzzles for theorists to explain. So one is changing pulsar spin frequencies over fairly short time scales. So this is not only the first example of this phenomenon, but the first accretion-powered X-ray pulsar ever discovered, CENX-3, showing quite large changes in spin period over a timescale of hours. And this is seen in more or less all accreting pulsars, including the millisecond pulsars. So secondly, the millisecond pulsar spin frequency distribution is very strange. So we see this kind of fairly abrupt cutoff where it's kind of somewhat uniform up to some cutoff frequency, and then you just don't see any more objects, even though the instrumental response would tell you that you can easily detect these sources up to a spin frequency for this instrument RXE up to about 2 kilohertz. The breakup frequency for these stars should be around 1200 hertz around here. So there's no particularly good reason why we shouldn't be able to detect things in here. And explaining why this abrupt cutoff is where it is very hard to do. So many things have been proposed, including kind of fairly basic magnetosphere disk interaction, which is the kind of thing I'll be talking about here, but also more exotic things like gravitational radiation. And then finally, jets from neutron stars. So this is something we haven't actually heard about all that much in this conference, but neutron stars do produce jets just like black holes. So for example, SCO-X1 here was discovered in 1981 to have this sort of morphology that looks a lot like an extragalactic radio source or a radio galaxy. You have a central radio core and these two lobe-like things here. And it was later shown to have these kind of slow ballistic ejections from the central core. And you can also see rapid flares in the X-rays, and you can see a flare from the core and a flare from things further out. And you can estimate what kind of energy transfer speed you would need to have to transfer energy from the core to these outer parts, assuming that the two are linked. And you end up with quite a large Lorentz factor, greater than 3. So it's a very relativistic jet. And then SURX1, another one of these Z sources, has been shown to have an even larger Lorentz factor, greater than 15. So not only do neutron stars make jets, they make very relativistic jets. And this is not just a few sources. This is basically almost all classes of accreting neutron stars make things that, even if they're not resolved, look very much like the kind of continuum radio jets that you see from black hole binaries. So you have all of your favorites, the accreting millisecond pulsars, the atolls, and the Z sources up here. And one thing that's interesting here is that it looks like the accreting millisecond pulsars are lying slightly harder in the radio at the same X-ray than some of the other sources, possibly indicating that maybe stellar rotation has got something to do with this. Okay, and then finally, so the ULX pulsars that Yuri talked about are rotating much more slowly, but they are also very interesting sources in their own right, and hopefully I'll be able to get to something related to them near the end of the talk. Okay, so the main thing I'll be focusing on is the global magnetospheric geometry. So basically, is the global magnetosphere mostly closed, so you have more or less dipolar field lines connecting the star to the disk, like in the Gaussian-Lamb model, or is it somewhat open, so you have these field lines which have been opened by differential rotation and magnetic pressure to large radii. And this is important because if you have magnetic coupling between the star and the disk, the two can exert torques on one another and they can exchange energy and angular momentum. And also because if you have these open field lines, you can drive a radio jet from the star. So simulations have been done on these and related systems like protostars for a long time. So for example, all the way going back to the mid-90s, people have seen things like these kind of magnetic field opening events, reconnection, flares, these kind of funnel flows that we would expect to have, and they've measured the accretion torque. And also people have found the kind of axial magnetized jet. So this is basically a magnetic tower that is being launched upwards by these torsional alpha waves. But one thing that has not been done by these groups is relativistic simulations. And this is interesting because in the relativistic case, the magnetic field itself conveys inertia, and therefore that there's kind of a minimum torque per field line that can be applied by an open field line, which is given just by the inertia of the electromagnetic field itself. So looking at some of these magnetospheres in a relativistic simulation, so here's an example for a fairly thin disk. Initially, you start with a dipole. You set both the disk rotating in a Keplerian way, the star rotating. The light cylinder for the star is out here, this kind of thin line that you can barely see. And basically what happens is you have flux opening due to generation of toroidal magnetic field. B phi squared gives you magnetic pressure, pushes everything open. You form current sheets which then reconnect, giving you these kind of nice reconnecting current sheets here, and ejection of these large plasmoids. And this kind of continues, but the most important thing is that what happens is a lot of the magnetic field is open. So you have very little flux that's connecting the star to the disk. This can also be done for thick disks, and even though you would not expect this to necessarily be as efficient in that case, you still find that you get quite a lot of magnetic field opening in the thick disk case. So what's happening here is that you're basically solving Maxwell's equations everywhere, but what you have above the disk is relativistic force field electrodynamics, and inside the disk, you're basically applying a certain current density, saying that you know what the velocity field of the disk should be, Keplerian rotation and some radial fall. So this is kind of a simplified system where you're using the force-free system, which is basically MHD with the magnetic field turned all the way up to be super dominant in the magnetosphere. And in the kind of disk region, you're just saying, I'm going to make a kinematic approximation because I know what it's doing. So what you find is this is kind of a grid of very simplified models in which I even turned off the accretion rate because the accretion speed because it was so small. And I set a constant conductivity in the disk. And this conductivity is the kind of turbulent, effective diffusivity you would expect from the MRI. So the idea was to look at how much magnetic flux from the star is open compared to the amount of open flux you would expect in the isolated state just from the rotation of the star alone. So the idea is you start marching your disk inwards from the light cylinder out here, inwards and inwards and inwards until it crosses co-rotation, and you measure in each case how much magnetic flux is open to infinity or to some large radius. And you find that it increases very rapidly. And if you make kind of a very simple model by saying, well, this is all kind of closed magnetic flux inside the light cylinder, it's going to more or less look like a dipole. I know how a dipole magnetic field behaves. It goes like, flux function goes like 1 over r. I can make this very simple approximation with this dashed line. And it kind of traces what the simulation does pretty well. You can do a better job by using an isolated pulsar simulation with this dashed red line. But what it tells you is that the amount of flux opening is pretty large. The efficiency of doing that is high. And also, if you look kind of equivalently at the torque applied by these open magnetic field lines to the star, it also goes along pretty well with kind of simple models that you could make just by approximating, say, a dipole field for the closed zone. So you can make a toy model and say, well, I'm going to approximate all the spin down torque and jet powers coming from these open field lines. I know roughly what that should do because I can say it's somewhat similar to a dipole. I know what an isolated pulsar looks like. I know the spin down power just goes like mu squared. This is the magnetic moment squared times rotation rate to the 4, or simply just like a rotation rate squared times the open magnetic flux. I'm opening more magnetic flux. This number goes up. And then the spin down power, or equivalently the torque, increases like the square of this. So by doing this, you can make a very simple model. You say, well, I know what an isolated pulsar does. I can make a simple model for how my magnetic flux is opened by interaction with the disk. Then I can say, well, the torque is just going to increase over its isolated pulsar value by the square of this with some efficiency factor zeta here, which we expect to be somewhat close to 1 if this is an efficient process. And then you can kind of put this together and say, well, if this is my only spin down contribution, and it only happens when this disk is inside the co-rotation radius, you can make a very simple model. Well, the spin down process happens when it's anywhere inside the light cylinder. You only have spin up from accretion onto the star by the usual amount when the disk gets inside the co-rotation radius. And you can come up with a very simple model for what you might expect the torque to be in this case. And one interesting thing you can do with this, you can say, well, if I want to have spin equilibrium, I just want to make these two things equal to one another, you just say, well, the spin up part is equal to the spin down part from this open flux. You rearrange it and you get an equilibrium spin frequency. And it actually looks somewhat similar to the kind of cutoff value that we saw earlier in the talk, so around 700 hertz. So one thing that's interesting is that so zeta here is the flux opening efficiency, this C is magnetospheric radius, this truncation radius divided by the classic alpha radius. If you put in, say, 0.6 for both zeta and Cassi here, the prefactor here comes out to like 750, so it puts you right in the ballpark for these kind of parameters. Another interesting thing is that if you're in instantaneous spin equilibrium from this process, you can rearrange things such that magnetospheric radius divided by light cylinder radius, almost everything drops out. All that is left is these model parameters. And then you can say, well, if I want to see channeled accretion, I need to have my magnetospheric radius outside the star. And that actually just gives you a maximum spin for accretion-powered MSPs if they're in instantaneous spin equilibrium by this process. And if you look at kind of these kind of reasonable values of Cassi, as we heard from Sergey this morning, this should be around 0.5 to 0.7 from observations. If flux opening efficiency is fairly large, 0.6, 0.8, it basically puts us in the ballpark here for giving this maximum spin frequency in and around the cutoff that's observed. Okay, if the open flux is collimated, you'll basically get something that looks like a relativistic jet, which is also easy to estimate. You can make the usual estimates. Say here I'm going to scale my m dot via the Eddington rate because I'm interested in explaining jets from these powerful sources like Z sources. And you get quite a lot of power. So if I have, say, SCOX1 or CRX1, where people have estimated that the jet power should be greater than 10 to the 35, by saying, let's take some fairly reasonable numbers here for these sources, and you can get a jet via this mechanism of a very similar magnitude. Okay, so that's all very well, but what you really want to do is do the problem more self-consistently and do the disk, basically evolve the disk so you're no longer making the kinematic approximation, the whole thing is evolving in a self-consistent way. So I'm next going to describe is a set of GRMHD simulations that basically solve the whole thing in general relativity in a much more self-consistent way. So the idea is that you start with all of your accreting matter initially outside the light cylinder. You're going to do it in a fixed metric, curve metric, with a kind of a fairly slow rotation that's appropriate for the star that you're interested in. And we want to have very high magnetization in the force-free or nearly force-free part of the magnetosphere outside of the disk stuff that's coming in. And that was the hard part of doing this, is keeping that highly force-free part well-behaved. So other important parts of the simulation is it's total energy conserving, so that means that you are including the effects of shock heating. And we have a relativistic gas equation of state, gamma equals 4/3, which means that this is roughly giving you what you would expect, say, for a ULX, where you have photon trapping and no radiation of energy out of it. Okay, so the equations we're solving are the equations of relativistic MHD. The important part here is that we have this B squared term inside our inertial term, right? So this is basically the non-relativistic limit. This is the half rho V squared, giving you kind of, this is the inertia. So now we have additional inertia from B squared here. So in the force-free stuff I was talking about earlier, you're basically saying this is much bigger than all of these other terms. But here we're going to keep all of the terms, including the inertial ones. I'm going to show the first simulation here. So we have the star. This is the light cylinder for the star once it starts rotating. Co-rotation radius is in here. This green line here is the last closed field line if the star is isolated. And then we're going to have all of our reservoir of stuff that can accrete out here, so at 3 light cylinder radii and further out. It's initially threaded by a magnetic field whose orientation is such that when it comes into the closed zone, the star and the disk field are anti-parallel, so they can reconnect with one another, and that'll become important. Here in this case, the stellar magnetic moment is 5 in units that the density of the pressure max is 1, so I'm going to be increasing this later on. I'm going to see what that does. So this is all our accreting stuff out here. This here is all our nearly force-free magnetosphere. So you set the thing rotating. You form basically something that looks like an isolated pulsar magnetosphere. This thing starts out in equilibrium but becomes unstable due to the MRI. Stuff starts to move inwards against the pulsar wind here. It starts to kind of push these field lines out of the way. gets closer and closer to the light cylinder and eventually crosses it, then you can see it start to reconnect here, right? And that reconnection allows it to get in more easily. And also these field lines here near the poles are getting opened because they reconnect and are able to be lifted out. So what's happening is the reconnection is allowing this sort of jet which is forming here to have a larger open magnetic flux than it would otherwise. So this is basically the enhanced pulsar wind flux opening thing I was describing earlier. So what you find is this kind of accretion funnel down near the surface. It's inside the co-rotation radius. You get this kind of thick disk that you would expect from, say, a ULX. Okay, so that's what happens when you have anti-parallel magnetic fields. So let's look at, this is just a snapshot so you can see mass density. This is toroidal magnetic field. So mostly at each pole, it's all coming in one direction. This is the kind of rotationally induced toroidal magnetic field that spins down the star. But you also have this one of the opposite side, which is very thin. And this is the, in this case, the accretion funnel. So this is the opposite. So this is pulling the star forwards and increasing its rotation rate. So this F thing here is part of how we do this force-free and MHD thing together. So this is a passive scalar that initially is only inside our reservoir of accreting gas. It gets brought in, and that allows us to do slightly different things in each of these two regions, allowing us to get very high magnetization in the force-free region. So you can see down by the star here, our magnetization, so magnetic energy density divided by rest mass energy density, is greater than 10 to the 4 near the star. And this allows you to do very clean comparison between the accreting and non-accreting states. Okay, so if instead of having anti-parallel fields in the star and disk, now they're parallel, and so you see something very different. And again, these are 2D simulations, and that's going to become important later. So you have parallel magnetic fields, so they can't reconnect against one another. And what's happening then is it's just forcing the stellar magnetic field down. And in fact, not only are you not increasing the amount of open flux, you're actually reducing it. There's additional field lines out here that were open that are no longer open. So that means that you might think, okay, maybe my jet mechanism isn't very robust because it's not opening fields in this case where you have some kind of large-scale field that's coming in that's of the wrong orientation. Okay, but let's leave that for now and come back to it later. So let's go back to our anti-parallel fields and just increase our stellar magnetic moment by a factor of 4 over what it was before. You set it running, and everything is kind of kept outside the co-rotation radius. Things kind of leak through every now and then, but more or less, accretion has been shut off, and you're in something that's somewhat close to the classic propeller state. It's outside the co-rotation radius, it's inside the light cylinder. You have stuff being kicked out by the stellar rotation. What happens is you have stuff that's threaded by magnetic fields. That magnetic field reconnects with the stellar magnetic field, then it's connected to the star, and the star is able to get rid of it by sliding it off centrifugally. So reconnection is very important in all of these processes. So now we have propeller. So what happens if you keep increasing magnetic field strength? Let's go up by a factor of 4 again, and by a factor of 8. So what happens now is that the stellar field is suddenly so strong that it can really start fighting against this incoming accretion flow. In this case, it's pushing it out. So what's going to happen here is that on the left-hand side, this stuff is eventually going to find its way through the light cylinder and kind of be in this kind of marginal state where it's just about in and out of the light cylinder. Whereas in this case, the stellar wind is basically winning, and the accretion flow is not able to get in. Every now and then it manages to kind of force its way through the equator in a sort of almost like an interchange motion by pushing these magnetic fields out of the way. But even when it does so and is able to get inside the light cylinder, it's very quickly kicked out again. So this can give you some very rapid transitions between stuff being outside the light cylinder, inside the light cylinder, and back. Okay, so we get 4 states: crushed, channeled, propeller, and excluded from the light cylinder. So what's most important here is that, well, firstly, magnetospheric radius basically follows the same laws you'd expect mu to the 4/7 as the kind of simple estimates. Secondly, that you, at least in the anti-parallel case, open up a lot of magnetic field, which gives you a jet power that scales very similarly to the simple model I described earlier. Okay, so in a kind of trying to show you some kind of preliminary stuff, 3D is important because you want to have a more realistic MRI dynamo, and because you want to be able to see the interchange instability of stuff as it tries to fight its way through the closed zone, the poloidal field that you find near the star. So this is a 3D simulation. So on the left-hand side, so what I've done is I've taken away parts of the sphere so you can see what's going on. So you have 2 vertical surfaces on each side and 1 horizontal surface. And then the left-hand side is going to be colored with toroidal magnetic field, the right-hand side with mass density, and the star is colored with mass density. So you set the thing going, and you'll see that. Why is this not going? That is strange. Okay, so what you should see is this stuff start to become unstable and flow in towards the star. But my computer has become unhappy with this situation. So we're going to skip that movie, unfortunately, and show you what happens here. Okay, so stuff becomes unstable, starts to spiral inwards, gets truncated by the star's magnetosphere, and then you eventually forms these accretion funnels here. But every now and then stuff is able to fight its way through in these kind of interchange modes, and you see these tongues in the equatorial plane here. So it shows you that you can have fairly stable accretion funnels at the same time as you have a certain amount of accretion into the equator. So this is just a 3D rendering of the field lines. So most of the field lines in the last simulation were mostly open, but the ones that were closed, that are interacting with the disk, are twisted back much more because there's much more inertia on these field lines because there is mass density threading them. These ones only basically have the inertia of the electromagnetic field, so they all have more or less the same twist. Okay, and then the last point is that we talked earlier about how the sign of the magnetic field in the disk with respect to that in the star was very important for opening or not opening field lines in the 2D case. So what this says is that in 3D that doesn't really obtain, because you have this is the electromagnetic jet power. The anti-parallel case where they can reconnect is in blue, but in the parallel case where in 2D the jet was completely killed off, now it's basically just as strong and it opens up and starts up just as rapidly as in the anti-parallel case. And the reason this happens is because in 3D now you can have these non-axisymmetric motions that can turn the field over, so it twists around and then it can reconnect and open up, so that the jet mechanism and the open flux mechanism seems to be fairly robust in 3D. You can do the same thing for an oblique rotator, but I think I'm running low on time, so I will go straight to my summary. And yes, okay. So in summary, we did some GRMHD simulations of accretion onto magnetized stars. We found the kind of 4 regimes you'd expect. In general, we find fairly efficient flux opening. And both the force free and the MHD simulations support the kind of simple model I described earlier for the torques and the jets. And the 3D is important, but for some of the kind of broad qualitative parts, the orientation of the magnetic flux that's applied to the system doesn't appear to be that relevant. And I'll take questions.
Questions, please.
Yeah, so you didn't have any time to talk about oblique rotators. I was actually going to ask about orthogonal rotators. Can you briefly explain a little bit qualitatively what happens in those cases? Can you get away without opening as many field lines?
So I haven't looked directly at the orthogonal case yet. So the oblique case, so this is 45 degrees. And I think, so this is fairly preliminary. I think you still open a fair amount of field lines. You still form a jet. It's still, everything is fairly stable. You get these kind of 2 streams, so your accretion system isn't axisymmetric anymore. In the orthogonal case, I would expect to get less field line opening just from geometric principles, but I haven't been able to directly test that yet.
Okay, one other really quick question. So what are the timescales of these simulations? Like these tongues of material coming in, are these milliseconds per frame, or can you get minute timescales for these tongues of material coming onto the neutron star or not?
Yeah, I mean, I'm seeing this on very short timescales. So there were, I think, 6 frames per spin period. So okay. You're looking at, very short timescales.
Something comparable to the spin rate. Yeah, okay.
Okay, more questions? I don't see Arthur any.
There's one up there. In the right.
Okay,
yeah. Can you show me the slide where you had the numerical scheme of your code? It was a very first or second slide. I want to make sure if you have some physical prescription for resistivity.
Yeah, all right. So that's way back here. Okay, this guy here. Yeah. So there's this is kind of a modification of the force-free system where I added some causal hyperbolic resistivity term to drive the system towards having a dissipative electric field along the magnetic field. So it dissipates alpha waves, but it doesn't dissipate fast waves.
Okay.
More questions? No? Let's thank the speaker again. And the next speaker, Yuri Kavecki, 20 minutes, including questions.
All right. Okay. Well, welcome everybody. This is the second to last talk. I will be discussing what happens during the type 1 burst, how the flame spreads over the surface, and this work has been done in collaboration with Yuri Levin, Anna Watts, and Jonathan Braithwaite. So very quickly, today, this morning, Valerie mentioned very quickly the type 1 burst. What are the type 1 bursts? They are very bright X-ray explosions that take place on accreting low-mass X-ray binaries. They are thought to be generated basically by the burning of the freshly accreted material. We care a lot about type 1 bursts because they are very bright, so you see them very well, and especially, as Valeria has explained, from the timing and spectral properties of the light curve, you can derive information about mass and radius of the neutron star. So we want to use them as much as we can, but to be sure about the result that we get from those fits, we want to be sure we understand exactly everything about the light curves. And everything starts from the rise of the light curve. So the basic idea is that you have accreted fresh material on the surface, but then the star is all approximately about to explode, but it will not explode all at the same time. So you will have explosion at one location, and then the flame will spread across the surface. However, one big problem about this is that the rise of the bursts are very fast, so you expect very fast propagation. But there are considerations that prevent basically the flame propagation to be driven by a detonation. So the main problem, the main conundrum is how do we get something which is gentle like a deflagration but still propagates extremely fast on the surface of the neutron star. I will show you here the movie. So basically this is how we think, that would be how we think that the flame propagates across the surface. This is a cut, a vertical cut through the burning ocean of the accreted material. Horizontal axis is the surface of the star, and vertical axis is the radial direction. Color scheme is basically temperature. So fluid that is orange is burning, is being heated, and fluid that is blue is cold. One thing that you should note is that there is a clear interface between the hot and the cold fluid. And if you notice, this interface, as soon as the flame has been set up, is always the same. It doesn't change. The dots that you see are simply tracer particles that will help sort of understand how the fluid moves. But mostly you see that there is motion along the interface. So to go quickly to the point, basically, one of the most important ingredients in this flame propagation, in this mechanism, is the Coriolis force. Here I plot the contour of the velocity of the fluid coming out of plane. So the idea is that the fluid has ignited at some point on the star, heated up, went up, it's expanded and moved sideways. But then what Coriolis force does, as does it with hurricane on Earth, it stops this motion, starting the motion perpendicularly out of the plane. So basically start a hurricane around the neutron star. Around the flame, which eventually propagate. Now, how does this help getting very fast propagation? It's basically a balance between time scale and length scale, and basically it's geometrical effects. So the Coriolis force has blocked your hot fluid, preventing it to completely spill outside, and you are with this slanted interface. This fluid is hot, this fluid is cold. And then what goes on is simply good old-fashioned conduction, which is slowly heating the fluid below it. So this is good. We said we don't want a detonation because we cannot get it. Okay, this is conduction, this is a deflagration. This process is relatively slow because it's conduction. But then the fluid heats up, it expands, and then it spills sideways again. The spilling sideways is very fast. It's basically velocity given by gravity waves. But this system spins at hundreds. My simulation here are done with 450 Hertz. So very fast. Coriolis force is strong and fast. So by the time the fluid has expanded, Coriolis force immediately acts, recreating the same configuration as before. This gives you an interface which is always the same and keeps on self-replicating. This allows you to have a long surface across which you can conduct. That means, because at the beginning people thought, oh, maybe if it is conduction, if it is a vertical front, this speed will be very slow. But if your front is like this, very horizontal, then you have an increasing factor which is given basically by the ratio of height versus horizontal length scale, and this would be 10 to the 4 versus 10 to the 2, say, centimeters and centimeters. So you have basically a boost of 10 to the 2 from the speed given by simply a conductive flame. And this gives you already velocity flame that are in good agreement with the observation. Coriolis force here plays another very important role, because I just told you that a vertical front would be slow, very diagonal front is fast. But then you may say, well, a completely horizontal front would be even faster in a sense. So if I let my flame, my initial hot fluid just simply spill across the surface, that would be even faster. The answer there is probably no, because you start with a little region which is igniting, and if you dissipate that heat all across the surface of the neutron star too quickly, then you kill the flame. So actually Coriolis force is very nice because it gives you this confinement, but let's say it doesn't exaggerate in this confinement and gives you good agreement with observation. But then if we play with different direction of propagation, so for example, if you check propagation in this direction, constant Coriolis force, you get some value for velocity, which is good. But if you try to go from pole to pole, because you want to engulf the full star, then you suffer from changing Coriolis force. And basically what we see in simulation is that anyway the propagation, despite being in relatively good agreement, would be too slow. But then, of course, we see, well, we put almost all the ingredients, all the physical ingredients we have on these systems, but we didn't put the magnetic field. And that's what we did. So we started doing simulations, putting magnetic field in the systems, but we didn't play with the value of the magnetic field, in the sense that we didn't fine-tune the magnetic field value. We just use the values that we think we see in this kind of system, in millisecond spinning low-mass X-ray binaries. And then we see that if you start with basically the lower end of the magnetic field, you see an interface which is roughly the same. Here the fluid is bending the magnetic field lines. The magnetic field lines give you some kind of back reaction. And if you, well, you didn't see it, but if you check the speed, it's actually going faster. If you increase magnetic field, configuration of flame changes. There are actually here we see a lot of instability going on, but the flame goes even faster. Eventually, if you put it too strong, the magnetic field, so this would be the highest end of the magnetic field that we see in the systems, you see the configuration is very similar to what we see without Coriolis Force, but actually if you check the time, this is the speed of this flame is actually slower. So again, to make a cartoon that explains what goes on, is that this I'm plotting cold fluid, hot fluid, okay? This thin line is the magnetic field. And basically the role of the magnetic field, despite the fact that this field is not as strong, for example, as that of a magnetar, is that it's providing me with the little mechanical friction in the vertical direction, which is balancing the effects of motion, of expansion, and of Coriolis force, that gives me exactly, or almost exactly, the speed I need to match the observation. And you can see this. So if I put a very weak magnetic field, well, nothing really changes because it's not enough to block the expansion in this direction. And when you start the hurricane, you would be winding the field lines, but eventually would start to back react because of tension. That's where the friction comes from. But if the magnetic field is too weak, it needs to be stretched a lot before it can back react. The flame has already passed. It doesn't have much influence. On the other hand, if you increase it enough, then, okay, we start the hurricane because of Coriolis force. I'm stretching magnetic field. Tension back reacts in a shorter time scale because magnetic field is stronger. That limits the speed of this hurricane. That limits the confinement by Coriolis force. And my interface will become more horizontal, gives me much of this geometrical factor. My flame goes faster. Of course, you see where I'm going. If I put too strong of a magnetic field, I will not be able to generate any kind of hurricane structure because the magnetic field back reacts immediately, but actually it doesn't matter because already also in this direction, the magnetic field is blocking the fluid. And so I can get kind of same inclination or even more vertical front, which would be slower. We tested this basically doing simulation with different values of magnetic fields. Ignore for a moment the red dots, red squares. The horizontal line here is the velocity of the flaming if you do it for a 450 Hertz rotating star without magnetic field. And you see that if I increase the magnetic field, the velocity stays the same, eventually goes up, when basically the two forces start balancing each other. Coriolis force, I mean, the time scale basically of reaction of Coriolis force and the time of the friction given by magnetic field balance, I reach the top, and eventually I'm completely dominated by the magnetic fields and the speed goes down. We did the same for a very slowly rotating source, this one at 11 Hertz, because this is a very important source, so we wanted to see what happens there. And again, you see that for very high magnetic field, the speed is completely dominated by magnetic field because the Coriolis force is useless here. And you see that the velocity agree completely in the two cases because it doesn't matter what the Coriolis force is useless. But if you reduce the magnetic field, the slowly rotating star actually keep following the same trend. This speed would be slightly like going like b to the -1, while the faster rotating star, the balance between the Coriolis force and the magnetic field goes on the side of the Coriolis force, and you get very high speed. Summary, I hope I'm in time. We now completely understand what's the physics necessary to explain the flame propagation in neutron stars. during the type 1 burst. And actually the answer is you need all the physics available. You need the conduction, you need the Coriolis Force, and you need the magnetic field. And also you saw there was this little motion of fluid along the interface. That is also important. That is due to the fact that the interface where the temperature changes kind of abruptly between hot and cold fluid, that becomes baroclinic fluid, and there is kind of instability going on. So when you put all this together, you get correct speeds. However, this simulation has been done in 2 dimensions. As we see also with Kyle just a minute ago, if you go to 3 dimension, troubles may start. For example, there may be instability going on, and we expect instabilities. Now the question that still remains to be seen is whether this instability will have effect on the flame, for example, making it faster, or maybe killing it because of disruption of the flame. But once we fixed also the last detail, then at that point we will be really in the position to be able to simulate ignition at different position of the star, different configuration of magnetic fields, and so on. We explore the full parameter space, and then we will be able to simulate first the full propagation, and second, basically simulate the evolution of the emitting pattern on the surface. And once you know the emitting pattern, you can do all the things as well that I mentioned before. So using, for example, the timing properties of the light curve, because if you have a pattern, your light curve will be a little bit oscillating. And through that, you can measure, taking into account relativistic effects, you can measure mass and radius of the star, which will help eventually to measure equation state.
Much. Questions? Sergey.
When we try to simulate flames, deflagrations, type 1a thermonuclear supernovae, the main problem is the turbulence which develops in shear flows. On one hand, it accelerates our flame, on another flame, it hinders good 3D simulation. What are your Reynolds, Rayleigh numbers, and so on? Do you ignore this completely, or can you estimate?
Yes, so one question that we have and we want to explain is, for example, you saw the interface is like this. The idea is, would, for example, Kelvin, the hurricane, for example, is very sheared. The velocity changes in the vertical direction. Well, quick answer is we have to try that in 3D. Longer answer is what we expect is, for example, Kelvin Helmholtz may develop, but we also expect maybe that to self-regulate. So, for example, here the transitions was very sharp. It may thicken the flame front, but eventually we think it will self-regulate, therefore sort of adjust, we hope.
More questions? Yeah, Jason?
Yeah, I have a much more naive question. So it seemed like your simulations, you were starting with basically a hockey puck of material equal thickness out to some limiting radius. And you want to get at something very, very subtle, and you want to eventually use this to determine the equation of state. But how reasonable is that assumption? Because you're talking about how the flame propagates in time, but how well do you know what the reservoir of fuel looks like to start with?
Yes. So as I said, yeah, that will be a little bit model dependent as well. What you expect is the fluid to be all close to ignition point. So, for example, how to set the ignition latitude, that is a little bit tricky. There are considerations that you can take, depending a little bit on the rotation, for example, of the star, and on properties of what you think is the burning regime. You may have, you can make estimate, for example, where the latitude of most likely ignition is. People think it's at the equator, but that depends on the spin, for example, of the star. And for the rest, you assume the rest of the fluid to be sort of all homogeneous, close to ignition. Does it answer?
Yeah, thanks.
Okay.
Thank you. More questions? Comments? no more questions. Then let's thank the speaker again. And now the last scientific talk of this conference, Alexander Moustakov.
Okay, I think that after talk given by Yuri Potanin this afternoon, we are all quite convinced that accreting neutron stars can reach the Eddington value and even more. They can be much brighter than the Eddington value. And in this talk, I'm going to focus on some specific details related to X-ray pulsars at extreme mass accretion rates. And I would like to focus on some things which I think would be important for further understanding of this kind of objects and for further understanding of ultraluminous X-ray sources. So X-ray pulsars, it's neutron stars with accretion in a closed binary system where the matter going from normal companion to the neutron star. Neutron stars are special neutron stars, X-ray pulsars are special neutron stars because magnetic field strength there is pretty high. It's about 10 to 12 Gauss or even more than that. And if we're talking about high mass accretion rates, then it's likely that accretion happens from the accretion disk. At some radial coordinate, accretion disk interrupts by strong magnetic field, and then matter follows magnetic field line and reaches the surface in small areas about 10 to 10 centimeters. And most of kinetic energy is released in X-ray energy band, misalignment of rotational axis, and magnetic axis results in phenomenon of X-ray pulsar. And indeed, we know that there is some sources with the luminosity above the Eddington luminosity. On this plot, you can see the example of a light curve of X-ray pulsar in small Magellanic Cloud in the outburst, and in the peak luminosity, in the peak of this outburst, the luminosity is about 10 times higher than the Eddington value. And also, recently, we have realized that there is some ULXs which are accreting neutron stars, and their luminosity by a few hundreds times higher than the Eddington luminosity value. Let's try to understand what happens in this kind of sources. When the matter is going to the neutron star surface at these small areas, it heats up the surface. And at high mass accretion rate, the radiation pressure becomes important. At some mass accretion rate, the radiation is so important that it affects the dynamics of the accretion flow. And at sufficiently high mass accretion rate, the radiation is able to stop accreting material above the neutron star surface. This problem has been solved in people tried to solve this problem in the late 70s, and you can see this expression for this so-called critical luminosity, which depends on mass and radius of a neutron star, of course, on the geometry of accretion channel, but also it depends on the effective cross-section of interaction between accreting material and radiation. It's important that this luminosity is quite different from the well-known Eddington luminosity, because the physical meaning of the Eddington luminosity is that the gravitation is compensated by radiation pressure. In this case, it's not enough to compensate gravitation. It's necessary to stop accreting material somewhere above the surface, and that's a bit different physical picture. The main problem here is to find the effective cross-section of interaction between radiation and material. We're talking about highly magnetized neutron stars, and it means that the cross-sections of interaction might be quite different because they are modified by strong magnetic field. Fortunately, we are able to calculate the cross-section of interaction between radiation and material. The main process there is Compton scattering, and cross-section of Compton scattering depends strongly on photon energy. You can see it on this plot. It depends on polarization. It depends on the photon momentum direction. It depends on magnetic field strength. And the cross-section might be much higher than Thomson scattering cross-section, or it might be much lower than the Thomson scattering cross-section. But for every magnetic field strength, if we know something about spectrum of the source, we can calculate the effective scattering cross-section, and therefore, for given magnetic field strength, we can calculate the critical luminosity value. And on this plot, you can see this critical luminosity, which is given by dash dotted line, and below this line, we have sources with hot spots on the surface, and above this line, we have sources with accretion column, where matter stops somewhere above neutron star surface and then slowly goes down to the neutron star surface. Of course, the sources below and above this line show different observational properties. For example, we know that in some sources we see the cyclone lines, and behavior of cyclone lines is very different for different sources, for sources with hotspots and for sources with accretion column. We know that, by the way, it's a spectrum of the same source in the different luminosity state. Even by naked eye, we see that the position of the line is different for different luminosities of this source. We know that for the sources below the critical luminosity value, there is positive correlation between cyclone line in the spectrum and luminosity. For the sources, for the bright sources which are above or below or above the critical luminosity, there is negative correlation between cyclone energy and luminosity. Recently, we have discovered transition of a source, X-ray pulsar VO332, from one type of behavior to the another type of behavior. First, we see positive correlation at low luminosity values, and at high luminosity values, we see the negative correlation between the cyclone line and the luminosity. It means that with this source, we were able to detect observationally the critical luminosity value. And on this plot, red line shows our theoretical predictions. The critical luminosity was detected somewhere here. So we see that our predictions coincide with the observational results. So what happens then? Then we have accretion column, and in the accretion column, matter stops at the radiation-dominated shock somewhere above the neutron star surface and then goes to the neutron star surface. The question is, how bright can be this accretion column? In order to find the answer in this question, we have constructed a model of accretion column in diffusion approach. We have assumed that we have a dipole magnetic field. We have assumed that the gravitation force is offset by the radiation pressure gradient. We also assume that the gas pressure is not important. The accretion column is absolutely radiation dominated. Then we can get the set of diffusion equations. These diffusion equations describe the radiation diffusion along magnetic field lines and across magnetic field lines. First, we get the photon energy density along magnetic field lines, and then solving diffusion equations across magnetic field lines, we can get that flux which is going away from the accretion column at every height. And integrating over the accretion column walls, we can get the total luminosity of the accretion column. Of course, these equations are not linear, and it's necessary to solve them in the iterative way. Anyway, it's possible to get the some kind of approximate relation for the luminosity of accretion column of a certain height. We see that, indeed, accretion column might be very bright, and its luminosity depends on the opacity across the magnetic field lines. If we would like to solve this problem really accurately, we have to take into account many things. We have to take into account that temperature in different parts of accretion column is different. If it's a case, then the cross sections in different parts of accretion column is also different. Solving this problem numerically, we can get the dependence of luminosity of accretion column on the accretion column height. It's given here in units of neutron star radius. Again, from observation, we know more or less that accretion column might be comparably high to the neutron star radius. Different curves here are given for different magnetic field strength at the surface. And we see that for high magnetic field strength, the accretion column might be very bright, above 10 to 40 ergs per second. We also see that accretion column cannot be infinitely bright. And it's easy to understand that. If the mass accretion rate is very high, then the temperature inside the accretion column is also very high. It means that the typical photon energy might be, is higher. And in this case, the cross-section, which depends on photon energy, at least in one polarization state, is high and closer to the Thomson scattering cross-section. As a result, in case of very high mass accretion rates, we lose at some point that benefits which we get from high magnetic field. As a result, we can get the maximum luminosity of accretion column as a function of magnetic field strength at the surface. It's given here by solid line. Recently was discovered a few pulsating ultraluminous X-ray sources, and our model can principally explain one of these sources. We think that this source has a magnetic field strength about 10 to 14 Gauss at the surface, and this prediction coincides with prediction which we get from propeller effect, which was already mentioned here. I will not go into details. And now I would like to say a few words about one thing which wasn't included in models. It's the accretion flow between the accretion disk and neutron star surface. Just from the mass conservation law, we can find the estimation from above to the optical thickness of the accretion flow along magnetic field lines from the disk to the neutron star surface. It's given here. You see that it depends on the velocity, of course. But if we will assume that the velocity is close to free fall velocity, which is not the case, but it's reasonable limitation from above, then we will find that this envelope would be optically thick due to Compton scattering there. And it means that in case of really high mass accretion rates, we never see the central object directly. Instead of that, we see that envelope. And it's interesting that the photons from the central object, they cannot penetrate through the envelope immediately. They travel inside the envelope for a long time, and after a while, only after a while, they are going away. It means that inside the envelope, we might have sort of thermal emission, and the temperature of this radiation inside the envelope depends on the luminosity, and it depends on the size of the envelope. And of course, it depends on the optical thickness. On this plot, you can see the inner temperature as a function of luminosity, and different curves are given for different magnetic field strength of a neutron star. Then the photons from the envelope penetrate through the envelope, and as a result, we have rotating magnetospheric surface where the temperature at every point is different. It's also important that the dynamics of the accretion flow in the envelope mainly defines by three forces. It defines by gravity, it is affected by radiation pressure, and it's affected by centrifugal force if we are solving the problem in rotating reference frame. In case of these envelopes, the radiation is not strictly directed anymore from the central object. And basically, it helps a lot to accrete material from the inner radius of accretion disk to the central object. Solving this, solving the dynamical problem numerically, we can get the velocity of accretion flow along magnetic field lines of the envelope. As a result, for given mass accretion rate, we can get dependence of optical thickness as a function of coordinate at the envelope. And also, we know the temperature inside the envelope, and we can get the temperature at every point at the magnetospheric surface. As a result, what would we see? We would see the rotating envelope, and it will produce roughly multicolored blackbody radiation. This picture gives us some idea about the maximum optical thickness of the envelope as a function of magnetic field strength. And it also depends on the luminosity. And we see that as soon as we coming to the luminosities about 10 to 40 ergs per second, the minimal optical thickness of the envelope is higher than 10. So the envelope is indeed optically thick. This conception of envelope around accreting neutron stars can explain a few things related to recently discovered pulsating ULXs. First, it's important that in this case we never see the central object directly. If the mass accretion rate is sufficiently high and if the envelope is sufficiently optically thick, then the spectrum will be well described by multicolored blackbody. And indeed, it's a case for the brightest pulsating ULX, which was discovered in galaxy NGS 5907. Also, the conception of the envelope explains the relatively smooth sinusoidal-like pulse profiles which we detect from ULXs, and which is not typical for normal X-ray pulsars. It's also explained why we cannot detect the cyclone line scattering feature. We just do not see the central object, we see the envelope. This envelope can also explain, probably it can explain the superorbital variability of ULXs. If the dipole is inclined to the accretion disk, then there should be precession of magnetic dipole due to interaction of the dipole with the accretion disk. For normal X-ray pulsar, the typical period of this variability is about 1,000 years. But if we are taking into account really high mass accretion rate, about 10 to 12 grams per second, we will see that period of precession might be about 1 year or even less than that. And now I would like to give my conclusions. We basically have some model of the central engine in the ULXs. We see from this model that it's a bit hard to have ULXs brighter than 10 to 40 ergs per second. If we take a look at the distribution function of high mass X-ray binaries over luminosities, we will see that at roughly about at this luminosity there is a cutoff, and this cutoff as a result might be principally explained by our model. And also it's very important that around ULXs and around really bright X-ray pulsars there should be optically thick envelopes which change a lot the observational manifestation of X-ray pulsars at extremely high mass accretion rates. That's basically it. Thank you for your attention.
Okay, thank you. Questions? Yeah.
So in this accretion envelope thing, I didn't quite get, did you calculate the depths along the field lines or across field lines?
Across field lines, of course.
Okay, so it's like, because in this, outside of this funnel flow, it's like an empty medium, right? So they would...
Yeah, it's just empty medium here, and I'm talking about optical thickness in this direction. Across magnetic field lines.
Okay, I got somehow an impression you calculated along the field line. And then the second question about this accretion column structure. So when the matter is sank through this radiative shock, it accumulates on the surface. It cannot much go across field lines, so we're building like accretion mountain behind the shock. Would it have any dynamic effect in the sources?
There was calculations on that, but not at really high mass accretion rates, and it is not really important. But still, there is lack of numerical calculations of accretion column structure.
Okay, more questions? Yes.
When you talk about the accretion column geometry, do you mean the hollow cylinder? And
yes, I'm talking about hollow cylinder.
In this case, what about the value of ratio thickness of column to the radius?
Basically, what we assume in our calculations, we assume that there is some certain geometrical thickness of accretion disk at the magnetospheric radius, and then we assume that accretion disk penetrates into the magnetosphere by this length, and then matter following magnetic field lines, and that's the way how we get the geometrical thickness of accretion column. Of course, there are some uncertainties, and it would be better to have some numerical simulations of interaction between accretion disk and magnetosphere. We understand that there is that uncertainty, but it doesn't affect much the final result.
Maybe it will be important that in very narrow, in geometrical sense, accretion column cannot be very high, because cannot have a large height, because the times of diffusion across the column is much smaller than the times of free fall of matter. It's qualitatively understandable, and this is results of direct numerical simulations.
Yeah, that's right, but I didn't see the simulations where we get a really geometrically thin column from geometrically thick accretion disk at the magnetospheric radius.
Okay, maybe the very last question, if there is one. No, I don't see. Okay, then let's thank the speaker again. And I pass the microphone to the chair of the local organizing committee, Peter Sternin.
Okay. First of all, we saw an umbrella. It's yours? I see. Okay. Very good. Okay. So, well, everything ends, and so our meeting is finishing, and I have a few remarks about it. So it was, 11th conference on neutron star physics here at TOF Institute. And now we had 116 participants from 22 countries, and who presented 62 talks with one remote talk and about 50 posters. And we see here that from 2011, that was the first international meeting here. We have some decrease of participation, but maybe we will not go as deep as here. Okay. So, and I hope that they had a very fruitful meeting, and the scientific program was formed by the scientific organizing committee was led by these people, so the George Pavlov, who is here somewhere, and by Dima Yakovlev, who unfortunately couldn't manage to go to the conference, but I think we need to thank them and all other members of scientific organizing committee. As was announced before, we will publish proceedings in a Journal of Physics conference series, and we will announce in a short time the details of submission. Okay. The details of submission. We think that the proceeding paper will be on average about 5 pages, but within the editors will discuss this and announce soon. We also ask you kindly to upload your final slides and posters if you wish, so they could be available to everyone. And I would want to thank the main people who made this conference possible. This is, as usual, Alexander Kaminker and Andrei Kashberov. They basically made everything here, so let's thank them. Sorry. And I also want to, briefly thank all other members of the organizing committee who helped us to have this nice meeting, I hope. So it's Denis Baiko, Serge Balashev, Oleg Baronov, Dima Borsukov, Polina Bivat, Mikhail Biznogov, Andrei Chagunov, Andrei Danilenko, Oleg Gaglichidze, Misha Gusakov, Lena Kantor, Anna Karpova, Slava Klemenko, Veronika Korzhueva, Ekaterina Lifshitz, Alexandra Mekhova, Dima Offengame, Dmitry Dmitrich, Alexander Potechin, Maxim Sergeyev, Yura Shibanov, Ksenia Telikova, Yura Uvarov, Vlad Yurchenko, and Irina Zemlyanska. Let's thank them again. And, finally, let's thank all the participants, all the speakers, all the authors of poster presentations, and other contributors. And we hope to see you again on our next meetings. Thank you very much. Sit.